So the other points stay the same, it's just that the z-axis
Yeah,
drops.
the z-axis drops.
No.
I don't know. I got negative. I got pi over 2. No, pi over 4. What's 40? What's 90? Pi over 2. Pi over 2 negative pi over 2. What?
Tell me I've been doing this homework wrong again.
I don't know. I don't know what I'm doing. So.
When I got there, I was like, I understand what to do. I just don't understand what the point is. Like, why are we telling me in words?
Because you want to be an engineer and you want physics and you want that stuff. I'm still trying to figure out where this fits into my major.
What's your major?
Finance.
Seriously, you need linear algebra for finance?
No, I actually want to be an actuary. So you need all these math calc classes.
You want to be an actuary?
What's it?
Can you program?
Huh? Can I program? No, I don't program.
You will later.
One of my friends
I
was,
don't want to program.
was an actuary.
It's boring.
And I was talking to him about it, and he spends a large portion of his day programming. And one of the things like that,
I hate programming. It's
I
so
can build
bad.
formulas in Excel.
that's basically what you're doing. Like when they do it,
no,
it's very,
it's like C
it's-
plus and.
it's very sloppy code. Like it's not supposed to be efficient. It's supposed to be something that's easy for them to update. I was like, that sounds horrible.
Yeah, but that's all Excel
Why did code
formulas.
is complex? It's
Huh?
really exact, and if it doesn't match, it's all wrong.
Well, I like math because I always felt math was black and white. And I wasn't in favor of language arts and reading because I felt it was
Same here.
it was kind of interpreted, self-interpreted. But I'm starting to find out as I progress through financial classes that there is no black and white in finance. It's all interpreted. You put in whatever numbers you want and you get the results you want. And that's all that makes it look good. That's
one
how
of
the stock market works.
crazy things about like when people are all uppity about politics, they're like, well, this number, blah, blah, blah. And then you can go and you can find this number, and then you're like, they're both true. Because, like, if I go from 1 to 10, it's a 900% increase, or I only went up by 9.
Yeah, but the way the stock market works, because there's so many,
Never tried to understand
like
this
you
stuff
have
like
Wall
that.
Street, you have Yahoo, you have MSN, you have like all these different types of websites that have all their different stock market ratings, betas. I mean, everything's different because it depends on if you analyze it annually versus quarterly versus monthly versus daily. So everybody uses whatever numbers they want.
I use quarter.
So if there's no consistency, the numbers never will match.
That's like when people talk about pandemics, they're like, oh, it's so horrible. 10 years ago, it was 1 out of 50 people were afflicted by this, and now it's 1 out of 10. Well, you changed your definition.
Yes,
No one
exactly.
knew. You just have a new definition. And you're a jerk.
But-
Story about that snail in Florida. Remember the snail?
I finally got a job, and I'm just hoping that it doesn't start before this math class is over, because I'm dying slowly.
Will they accept a corpse?
I don't know. Haven't asked.
Find out, because maybe it won't matter.
All I know is I told my friends at the end of this semester, this book is going away.
Can't tell you because it's an IS edition, and I highly doubt anyone's going to take Calculus 3.
Nobody will want it.
No, I'm saying, yeah,
Yeah.
chances of Calculus 3 and it's an IS edition.
Well, apparently there's 7 out there, right?
I don't know why they make it specifically for international. What's the difference between the international edition and the normal edition?
We speak Japanese.
This one uses metric instead of
Really? Is
Yeah.
that the only difference? Shouldn't everyone be using metric?
I don't know.
They should. What's that got to do with anything?
I don't know the length of
If that's
the
the
year
difference
versus the
between these
length of the
two
yard.
books, everyone should just use metric. Especially if
Everyone
you're doing
should.
Calculus 3.
I'm totally making that up.
I-
I have no idea.
I
If that was true, I'd be...
You know how when you're driving down Tokyo and you see like 500 meters construction starts, I'm like, what's a meter? I don't know. Tell me 5 miles and I can tell you how
I
far
judge it by
that is.
how far I used to run. I'm used to running. I've never ran.
So I made a big mistake yesterday, or the day before, Saturday. I slipped my SD card to my camera into my husband's brand new Mac computer into the optic drive, and I lost it in there. I couldn't get it out.
Wait, you put the SD card in the optic drive.
Yes. The
The
SD
has a hole, so.
no, not on the Mac. The screen that you slide on.
Well, I don't own a Mac, so I don't know.
No, the optic drive is up here. The SD card drive is right underneath it down here.
No.
And I've done it so many times. I did it without looking, and I just went bloop, and there went.
So wait, you want to push a button to open the optic drive?
No,
You have to unscrew it, take it apart.
we didn't touch it.
No, if you do that, you lose the
It's not gonna work
warranty.
till you do.
Well, we took it back to the VX, and
Yeah, if you unscrew it and open it yourself, you lose the warranty.
yeah. So we took it back to the VX, and they wanted to give us a check for a brand new one, and I don't want the check.
Why?
Because there's stuff on my computer.
So you can always take out the hard drive and then just put it into the new one.
I don't want to touch it.
If she's not willing to unscrew it, take the card out.
I don't think it has screws
Well, no, but see,
either.
if the person they got it from is doing it themselves, your warranty should still too.
The Mac has no screws anyway, I don't think.
There's a way, they have a way to open it. I know I have a friend who does it. I'm not sure how he does it though. Cause that's what he did with his, MacBook Pro.
I saw you take a giant magnet to it.
So I was in WebTecho yesterday, and I see I have a message, and I'm like, oh, what is this? I go open
forgot
it.
my website password.
It's the test, and I'm like, ah! I'm like, I'm not touching that.
Did you send it out already?
Yeah,
Uh,
I did.
As I said, I forgot my password. I haven't touched it that long. And
It said warning, 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 and I said, holy cow.
Tracy demo. Tracy demo.
Have you heard about Optic Rift? I think is what it's
No.
called. It's a VR glasses,
Oculus Rift.
Oculus Rift, and they have two separate screens, and the screens are all jacked up. Like if you looked at them by themselves, you're like, this looks retarded. But they put two lenses over it that are like fish-eyed, which gives you like 120-degree vision. So you get the sense of motion because instead of being limited here, it's going like here. You can get. Well, I guess they haven't got motion sick. Like they put people in it who do get motion sick, and they're able to wear it for like 30 minutes. They're fine. There's like old people or people's old parents who are like, man, this is just like Italy, like places that they've been and they render everything. They can't restrain themselves from reaching out to try and touch it.
Supposedly Doom 4 is supposed to run on the Oculus Rift too.
Have you ever experienced a D-Box seat in the movie theater?
No.
D-Box seat?
No? Oh my god, those are so awesome.
What's a D-Box?
It's a seat that moves with the movie.
Oh, you mean like they're doing like the Universal Studios?
No, it's in a movie theater. We have them in San Antonio all over the
No,
place.
but I'm just saying
But
like
I don't
those,
know.
like those rides.
Yeah, I guess, yeah.
Why a movie theater would want to move around.
They're cool. We went to go see the new release of Clash of the Titans or whatever it is when we were back in San Antonio. When it first came out, and we sat in those seats, and they just kind of, as the boat rocks in the movie, the seats rocked.
It's pretty awesome.
So.
I'm going to go to Austin this July
They'll have them in Austin.
for a convention, so I'll probably check that out.
Mhm.
I'm really
It's definitely more expensive than a movie theater ticket.
I'm really
It's way
excited.
more.
Well,
Iron Man 3 is
convention's
coming
only
on Friday.
$45, which is like 200% discount from a normal convention.
Well, your comment got lost, you couldn't break into that conversation.
So apparently, if you have 6 people circled around, they can all have one conversation. But if you have add a 7th person, then they'll break into 2 different conversations.
Something to do with even.
That's right.
No, 6 is just the max. Like 8 people
That's
is gonna be 2
known by
conversations.
project leaders too. That's why they don't want to get cliques and subgroups in their project. So you have to keep that in mind. But in here, we can do it with 4, break into 2 conversations with 4. We could probably do it with 3, as a matter of fact.
We just keep on finding the derivative.
Yeah. Okay, we got to start in about 10 seconds. And there's just one thing that should have been pointed out last time, so I'll remedy the situation now. It's about the gradient. And if we have this TP, which is a function z, which is a function of the xy position that's on the floor, and we want to know what is the directional derivative as we move across the top of the curve in some certain direction such as that, such as this, then that direction will have a projected line on the xy plane, and that projected line on the xy plane is what we're taking as our direction of motion. So if on the xy plane we want to move in this direction, and it's a unit vector which is u1 I hat plus u2 j hat, and then we have defined another direction in terms of the surface of our TP to be the direction of maximum steepness. And that new direction that we define, in this case it would be going straight up, it would not be going to the side or down. So this would be what we call the direction of the gradient, which is the direction of maximum change of our height as we go. But the actual gradient only refers to the direction that you have to go to achieve that maximum growth in elevation. It doesn't refer to your direction up the mountain. It refers to your compass direction back in the xy plane. In other words, if you're at this point and you want to go to maximum growth, then you go forward in this direction. You don't worry about the upside of it. You just take the xy part as your gradient. So the gradient for this would also be a two-dimensional direction. So the del f or del z would also be in the xy plane. It would only have an ij part. It's not a three-dimensional gradient. Now, you can have other functions which do have a three-dimensional gradient, because here the function that we're examining is one of the coordinates, z. So its gradient is only the direction of the other two coordinates that you need to move in. But we have other functions that involve all three coordinates. For example, the temperature in this room. The temperature here is a function of my three coordinates, x, y, and z, true? Temperature here is a function of my all three coordinates, x, y, and z. So if we're at this point and we want to know the function, the temperature, then it's a function of x, y, and z. So the gradient, which would be a vector pointing in the direction of maximum increase, would be a three-dimensional vector, agreed? Not a two-dimensional vector. So you do have three-dimensional gradients and two-dimensional gradients, even in three-space, depending on whether one of your variables is the function or whether your function is a function of all three variables. So that needed to be pointed out. Now, yes, sir?
What's the directional derivative? Like conceptually, my numbers can't match the back of the book, but I don't actually know what it is.
Okay. A derivative is a rate of change. So if we take the temperature in this room, I know the temperature right here, and if I move to another point, it's going to have a rate of change. But that rate of change depends on the direction that I move into. If I move in this direction, it's going to have a certain rate of increase, agreed? If I move in this direction, it's going to have a certain rate of increase. So its derivative, or rate of increase, depends on the direction that I go in. So you can't say that this point has a derivative with temperature, because that derivative is unfounded until you specify in what direction you're going, because the derivative is a difference between 2 points, isn't it? It's a rate of change of 2 points as they collapse. So it involves 2 points, not 1 point. So you have to name the second point, which gives you a direction. So you can say the temperature is increasing or decreasing at a certain rate as I go in this direction. So the increase or decrease is known as the derivative of the temperature, and since it's as you go in this direction, it's a directional derivative. So it's a derivative that is that is calculated in a certain direction that you can go. Now here we have a surface or a function that is using one of the variables z. So if we want to, if we're at this point, and if we're at this point on the mountain, then you go down to the xy plane and you see what your xy coordinates of that point are. Now down here in the xy plane, then you ask a question: what direction in the xy plane do I have to go into to achieve the maximum growth? And that is the direction that you go into, and of course you'll be elevating up the mountain as you go in that xy direction in a maximal sense. But as you're at this point on the xy plane, if you go in different directions in the xy plane, then on the three-dimensional surface you will acquire different rates of growth, agreed? So your derivative is your rate of growth, and it depends on the direction that you go in. So therefore the derivative is called a directional derivative. And the maximum directional derivative is known as a gradient.
Okay.
Okay, so there any other, those are exactly the right kind of questions to ask at the beginning of the class, which are to review and solidify our concepts and logic. So are there any others in that category? Okay, let's do a little administrative stuff then. Test 2, so I need all you guys to sign off on the test 2 instructions. Just go out to the test 2 conference and say, yeah, I understand the instructions, and then I will release the test to you. Sometime tomorrow, as soon as it's completely formed. I hope you weren't planning to take it at 3 a.m. or something.
3 p.m.?
3 p.m. is pretty clear. The test will be out by 3 p.m., okay? If that works for you. Then that's your 24-hour span, then, right? Okay, so it'll be due in 7 or 8 days, next Monday or Tuesday, as we've indicated. And it'll be remarkably similar to the first test, which it will have about 12 longer questions and about 30 less than long questions, or just long as you want to look at them. So the first test was a little long, so what I'm going to try to do is to make the test bank questions quicker. And as soon as you zoom in on the multiple choice, there's no sense doing any calculations. You get full credit just by choosing the correct letter for multiple choice. So as soon as you're sure of it, just write the letter down. You don't need to actually do a calculation as long as you're sure of it. It doesn't involve any extra points there. And I'll try to make the short answer questions to be actually shorter. But I've chosen one problem from each section in the text. And those I can't make much shorter because those are text problems. So that's where everyone crashed and burned last time. So there's not much to say there except maybe do those first while you're fresh and give yourself lots of time. And maybe I'll even put them in the front of the test to encourage you to do that. And do the multiple choice short answer later. Okay? So the first test and the second test I've decided to be 25% each of your grade, and then 34% will be the final. And the other 16% comes from posting YouTube videos
I'm all caught up.
for your classmates to look at and critiquing theirs.
You can go on my website, what password is.
He's good.
Well, some people don't want the 16 points, so it's always a personal choice. And,
What sections does the second test cover?
it covers 11. It covers 11.4, which starts the cross product, through the one that we're doing the whiteboard on tonight, which is 13.6.
Okay.
I went through and I was also watching a lot of those videos. It surprises me how I sound on camera.
Really?
Yep.
Interesting.
I already know what I sound like on camera.
I
Well, you
haven't
okay.
looked at them.
I sound horrible on camera.
Okay. Well, for what it's worth, now you know. That's right. Also, people react the first time they see a photograph of themselves. And especially from the side, and you get the posture and all that stuff too. And the back is sometimes even worse, because usually we spend our whole lives just with a frontal mirror view. We have no idea of profiles or things like that. So all that, yeah, is revelatory. It's true. Now, starting with tonight's homework and our whiteboards in the next class, you want to be meticulous, because the final exam is going to be drawn from these homework problems from now on. And you definitely want to have good solutions. No more of this wave of the hand and move on to the next problem that we've been enjoying for 6 weeks now. We're actually going to have to crank out answers so that you can ace the final and pull your grade up to where you want it to be. So I guess the final will be the last night of the course on a Friday night, and we'll spend the probably almost all the time on it. We might do a little whiteboard when we first come in, and then we'll spend the remainder of the time on it. We can even go an hour over from 9 until 10 if you want to. And I'll try to make a reasonable number of questions within that time slot, probably no more than 10 of the homework questions, max 15 probably. And they'll all be from the material that's still in front of us. Okay? So that's where we are administratively.
We're not gonna be able to come in earlier that last day to do it?
Yeah, I can always do that, as long as you're still here when class starts, so that there's no loss of control.
Okay.
You can come in early and just stay here. That's true too.
If we come in earlier, can we take longer if we need longer than 2.5 hours?
Yeah, I'm not worried about the time.
Okay.
As long as other people don't object, that's not very In fact, we can take the whole test in the afternoon when we want to. So we'll talk about that more as it gets closer.
What time do you get here? Around?
Friday,
after 2?
Free day, I can come anytime.
Okay.
Okay, so it's been a very successful class, and I'm real pleased that you guys signed up, so it actually went, and that Dakota allowed it to go. And it's been a really complicated subject as it's turned out, so I think it's been successful. Okay, so is there anything else that we should mention or talk about before we jump into these particular whiteboard problems? So we're on section 13.6. We had 2 sections today, didn't we?
No.
Just one. And the title was Directional Derivatives and Gradients. Very, very important. Title, topic, section 13.6, page 957. We'll check 1, 2, 3, 4. Volunteers.
I'll do one.
I'll do 3, 2. 2. Oh.
I got half a 3.
I can figure out the last 2. I did 4 then.
Okay, they're done. Now problems, there's sure a lot of them. 2, 3, 6, 12, 15, 17, 23, 28, 33, 35, and they're all important. Okay, you're each going to get a color. Red, blue, green, and black. So come up and circle the ones you want with your color. Red, blue, green, and black.
How many?
Till they're gone.
Oh, jeez.
I'll go one at a time.
Okay.
Keep going, Stuart. Keep going.
I picked the highest number that I got it to.
Notice you strode up to be first.
I didn't want to get stuck with problems I
I
didn't
know.
have. Then that's
See
always
that
more.
coming.
That's always more confusing.
Yeah, how many did you do? 4, let me see.
4.
4 more.
Were you gonna collect homework?
Eventually.
What is it again? 33, 48, 6.
I think you should just break these breaks off.
That's a great idea. I guess that's why they're called bricks. They're pretty much my boards, so I certainly be entitled to. You never use them,
We use them all the time.
unfortunately. Oh, seriously?
No, unfortunately.
Unfortunately.
I use my boards like crazy.
No,
Breaks.
the breaks.
Oh,
Like it's uncanny how often
I know, you step on them.
I have big feet, apparently.
Okay, so let's make ourselves proud of these solutions now, because this is important stuff. It's not like linearization. This is basic.
It's, not half it.
Okay.
I'm gonna do 17.
The first half is
28.
more important.
You
Oh,
did 17?
instead of 28, yeah, I'll trade you.
Okay, then I did 28.
28 was the one that I didn't understand in the direction of the x-axis.
Okay, I did 28.
Please write your page number and problem number for
Monica?
future generations, so
Why are you looking at
when
me?
they look at these tapes, they have some idea what you're doing.
Is it each column or just a general column?
No, just once on the board.
Okay.
Well, we got most of those knocked out. Nice going, guys.
I just think it's 74, 41, 42.
So I'm pleased the way this.
Just have a little bit of 42.
Okay, a little bit's better than nothing. So I'm pleased with the way people stepped up and took some of these.
improved.
in the last 48 hours. What, did it smell the barn or something? This is very neat color coding. Know what they do. You're fine.
Is that right? Two
Uh,
per square root is 21?
I'll let you know, just keep going, because no sense losing momentum. That's gross.
Not good?
Where'd the 21 come from?
The square root of, yeah. So it's 25 minus 4 is 21.
What?
5 squared, your
Yeah.
absolute value,
And what's minus 2 squared?
is 4. Oh, it's
Plus.
plus 4. So it's 25, 29. I always miss those
I'm
out.
glad the door's closed. The Math 103 students.
Is that all that was wrong on it?
Yes,
Okay.
that's all that was wrong with it.
So my operations are right.
Yes, your
Okay.
calculus is impeccable.
Okay.
Your arithmetic is,
Not so much?
never has been.
All right, that's okay.
You don't mind.
I don't care.
Okay, while we're talking about this, this is just one number, it's not coordinates, so it's just an 8. It's a
Oh, it's just
quantity.
an 8, it's a quantity,
It's a
okay.
quantity, yes. Yes. Okay. Just little nitpickies, you're doing fine. You're doing really fine. Two fives.
What's the symbol for gradients?
Del F.
Del.
Upside down.
The upside down triangle.
Yeah, that's it.
Oh.
Guess you didn't read the book, huh, Stuart?
Don't bring that up. We read the book a month ago and we're just going to count our blessings.
I actually,
Yes?
my entire first page is just the examples. I did all the examples.
That's awesome.
I don't understand a lot of what
Glenn
the words
Stewart
mean.
did the examples.
I'm always having problems with examples.
Some of the examples are not helpful. They're like, as an example, consider this shape and pretend, if you will, that we'll use symbols for the duration of the example.
You're
And I-
facetious.
No. I will find it for you.
It's just the wording of how they do things. I'm not sure recording.
35, did they actually ask you to evaluate this in a point? Well,
No?
I think they just wanted a functional relationship, at least.
Is it, does that say xi over x squared plus y squared plus z squared plus yj?
Well, you did it right. That is the gradient. Well, if you start with F, you probably end up with W. You probably end up with del W, but
Oh, sorry.
yeah. And then this
That's
is 39. Oh, okay. I caught up. Yes. Oh, that's perfect. Del W. In fact, all three of your problems. And 39 is also perfect. And your 23 is perfect.
I had a very big weekend.
Just everything
So wait,
is
it's
gold.
not 2x, 2y, 2z?
No, it's not 2. The 2's go away when you take derivatives. You've heard of derivatives?
Yes?
So the 2's cancel out when you take
X-
derivatives.
It's x.
Yeah,
Oh,
because,
just a square root. About, I don't
I
have
gotta
the
miss
square
you, I
root.
gotta miss you, oh, I gotta miss you. So, here we have 36.
I'm not sure how. All I know is that Y and Z were the same.
Okay, there's a piece missing. Okay, now the piece missing is when you take the derivative of u, you have to also take the derivative of the inside, which is going to give you 2xy. So this piece right
Mine's
here,
got paper plate.
36,
I use,
2xyz.
I sit with this in my
Missing
lap a
that
lot,
piece.
because my desk is very small.
You're missing
Doing
that
homework
piece.
like
When you
this.
take the derivative of this,
Uh-huh.
because it's a chain rule,
Oh,
okay?
that's right.
Yeah, it's a chain rule.
For a
I'm missing
second,
that
I
piece.
almost asked, where's your camera?
Okay?
It's in my purse.
But it was
So
not
that
my
piece
camera.
has to be.
It's a different camera. Is that what's on top?
Okay, so this is nailed, that's the correct gradient.
Those are all right.
And the magnitude of that, you testify is, your final
Square root
answer.
of 145/4.
Well, this, yeah, that's right. Well, this is the directional,
I think it was S P, right? I just had,
well, what they want finally is the magnitude, they wanted it at 2,4. Would you do it at 2,4?
Yeah, very easy writing. I need an mechanical pencil.
Every part looked right, so I'm not gonna worry about that. You got this one.
I was
that's
I
doing
go
it.
through so much that I would go insane if I had to sharpen.
I write
evaluated this
too
at 2-4, but they wanted it to,
Well,
My
Um,
question is, on this one,
it'll be the same.
why is
Yeah, you
it
can do it that way
not
first.
squared? I see the
Um,
line.
what was the final answer?
But what happens to the Z?
Yeah, you can do it that way first.
So it's product rule.
Yeah, so it's the same. So
Basically,
it's,
um,
this is
there's
9
no X
minus,
there, so it pretends like a
1/16th, right?
just disappear.
Mhm.
so that's what it's gonna come up. Okay, so that's just arithmetic. Don't worry about that next week. And, I'm not sure you'll get these magnitudes all the way down. Here, this is e cubed minus sign, and otherwise perfect.
It's a negative?
Yeah, but otherwise perfect.
Okay.
Okay,
Do you have a question on number 72?
72.
Yeah. So 72 is not like I wanted to see. I have -2 square root of 5 over 45.
Negative what?
No,
2 square root of 5 over
in spite of that
45.
noise, no.
Oh, that's how off that is.
Negative 2 square root of 2 over
Square
45?
root of 5 over 45.
Well, 45 can be reduced to 9 times 5, so it looks like it's going to come out the same. You just can take the lowest terms. Square root of 45 reduces down to 3 times square root of 5, okay? Square root of 45 is not yet the lowest term, so I think you have the same answer. It means that you're entitled to put 72 up there if you want to. So, most of this work looks quite good. There's a couple of arithmetic mistakes that aren't serious. So, it all passes muster.
You know what I hate? I did these all correctly, but still looking at the symbols, I have to remember what it was I did, because it's still confusing.
Huh?
42.
Maybe maybe.
Oh, this is where I stopped, you actually found it. Oh, different number, 39, okay, I have 5 as 39 also, but.
What's the first one on here?
17,
17.
I have 39. That's it. Yeah, I don't remember anything of what I did.
Well, I think that 42, we're gonna have to do from scratch. Okay?
Yeah, I thought it was 42 and 41.
I got 1/2 I plus 1/4 J,
That's winner,
that's right.
42.
I just don't know how to graph the,
Can I take a picture?
this one?
Yeah.
I just don't know how to graph the vector. So, I'm assuming that it's because it's positive and positive, I goes this way, J goes,
It's that simple.
I goes down towards X. But it's a 2-dimensional and then,
Here's everything.
I didn't even do a curve.
Oh, it's a parabola, y equals x squared. And then you find that point on the parabola and you draw your little,
Going towards the inside of the,
well, 1/2 I plus 1/4
which
y.
goes up,
Yes,
gotcha.
got it. Good answer sheet. So you want to put 42 up there in case anybody else wants to see it? Yeah, we'll put it in your space down there.
Yeah, we're done.
Okay, so that's well done. It's impressive. Now let's,
I'm just dumb sometimes. Sometimes
you were waiting for 6 weeks for a chance to say it.
I did. But I really feel like I'm following.
No, you felt that way since I mentioned it.
I
No, you aced 107 and you were just
Yeah, but I had the book.
surfing and cruising.
What is 107?
Algebra.
I guess I can't do C1.
College
I got
algebra.
62, not 72.
Okay, so now where did number 6 go?
You got
south?
6, oh.
I guess I can't do 6.
Um,
So that's the 41.
Mm-hmm.
Yeah, that's what I want to do.
Y, Z,
492, right? Oh, do I just leave it like that? I don't have to do anything?
Yeah, and then you just had to graph it. And since
So
this
I
one,
did.
yeah.
Because I was doing something, I was like, I want to do something after where I found the magnitude of that. Looks like I didn't need to do that. Maybe that's what it was.
Sometimes I feel very, I don't know what the final answer is supposed to look like, so I'm gonna do everything.
Got it right in the first place. Which looks something like that.
Hi, so. Okay, so we have to look at these derivatives here because there's a piece missing. Yeah, when you take the derivative with respect to z, there's this piece too, 3z squared plus, right?
Oh,
No, yeah. Yeah, right, okay. So Monica did a nice job on 42.
Did anyone do 72 or 74?
They might have to come down to me, because
I still don't trust my answer with 72, even after you looked over it.
maybe I should do this.
I didn't look at it, I just don't see how it matches.
You just didn't reduce yours all the way. I think it'd be better if you did it though.
Yeah, if
I
I
can-
Well, no, this is just calculus, there's no, I mean, this is just calculus 1, there's no,
I can read his handwriting.
there's nothing,
That's true.
there's nothing, there's no calc 3 in that question. So let's get these immortalized. So here we have some very good solutions to 4 or 5 problems. So AJ, could you square that board off in this direction so we get a good camera angle? And here, here we have good solutions to about half of these problems. 42 is wrong, and 6 is wrong, but the others are right.
42 is wrong?
No, not yours, Lynn's.
Oh.
Okay, so that's this side. Let's go to the other side. That's nice.
Has anyone seen
Need to resquare the boards.
what is his name? There's another YouTube channel I found where the guy, like, he really doesn't care about tutoring. He's like, yeah, I'm just gonna do it the easy way, 'cause that's how I like doing it. I'll go ahead and write DRDU, because that's what the normal math peoples like to do.
Does he look like a guy who wouldn't be doing math at all?
Very nice.
No, his voice sounds like he's a guy who wouldn't be doing math at all.
Yeah, like, does he look like
School Chuck.
Yeah.
Yeah, I haven't seen him, but he's really funny to listen to. And then Dr. Bob. Dr. Bob is very difficult to listen to.
Hard to understand or boring?
36. And this is
He is very boring.
48.
Monotone board or
Just a
just?
little bit too.
I don't know. And he has a stick, and he like points at everything with the stick and it goes down. I really like Patrick JMT, because he's
Yeah.
like doing everything slowly.
I like the people who do it like on a PowerPoint or a slideshow. I don't like that.
So this homework was quite
I pretty much just
successful.
got to practice
this right?
JMT.
Yes, this is the answer right here. I don't know what that is, but this is the answer.
That is just me writing stuff.
Yeah, it's in just right here.
I found my error. Would have
It
their
makes me
zero
feel
and
better
zero
when I
line.
write stuff.
Aye, miscopy
The
problem.
exact one I did was 41. I just
Fatal.
added stuff to it. I'm just set up, trust me, 72. I have a knack of not trusting my answers. They're usually wrong. And that,
Our answer is really important.
yes.
Okay. So let's see if these problems really are Calc 3 problems, or they're not really worthy of the front board. So we're contemplating 72 and 74.
Is it
The
9/7?
temperature at a point in the
No,
plane
this
is,
is
find the rate of
Because I
change
got
in the
these
direction
two
of
numbers,
this,
but right here, I
Yeah,
got
this-
162 or something.
I have to.
and that wants you
Ah,
to look at the
cubit.
direction in which
Yeah,
the temperature
and this is
drops
pretty
most
good.
rapidly.
Okay.
Yeah.
Find a unit vector in that direction. Well, that's just a little bit of calculus 1. So I fail to see the problem in 72. Maybe you guys can't take derivatives.
You know, what was the answer for 72 again? I'm not prepared to my answer. Again,
I didn't get that far.
that's the,
No, sorry.
Well, exactly what was the problem in 72?
well, I
And
have,
this one's right?
I just don't trust my answer. I don't know about everyone else's.
Well,
I don't stop.
first you take the directional derivative, true?
Yeah.
Yeah, because you have to multiply by 1.
And this is not yet a
Yeah.
unit vector, so you have to normalize it to a unit
So
vector.
you have
A,
to do 20 times.
And then you have to dot it into the gradient,
Yeah,
after you
because
take
you
the
have to
gradient
do
degree.
Yes.
Is that
And
the one where you do the absolute value?
then when you
of
dot
the
them together,
differential?
Well, I just feel like I did it after mid
Yeah,
error.
stop.
That's what I was.
Yeah, I-
you feel like
Where
what?
you- I stopped,
did
I got
it
that same
as a
thing.
Error.
Again, one more
I
time?
did something wrong with multiplying.
Oh.
That's what my fear is, just simple math.
Well, are you paranoid about it enough that you would like to actually see it done? Yeah, please.
I just need the answer to compare.
the answer to 72 is 1 over 9 root 5. And I think your answer's the same. Please tell me what your answer is.
2 square root of 5 over 45.
2 square root of 5 over,
45.
okay. Is you sure it's not the square root of 45?
Yes.
You sure?
Yes. That,
Okay, so this is 2 square roots of 5 over 9 times 5 times 5, which is 2 over 9 square roots of 5. And the book answer is 1 over 9 square roots of 5. So it should be 1 over 9 square roots of 5. So you see how close you are? There's just a 2 there instead of a 1. Right?
You did twice as much as you needed to.
So that's just a silly 2, you know, so we're not gonna spend 20 minutes locating a 2, because you
and
did it
this,
right.
Okay, and the minimum just means I take the negative form of that?
Yeah,
Okay.
you go, oh, well, no, you have to do it backwards. So for B, you just work with the gradient, and you take the negative gradient. Okay?
So,
So A is a directional derivative,
yes.
and it involves the gradient dotted into this A direction. But B involves only the gradient.
Okay,
It only involves the gradient.
okay.
So you take the negative gradient. What can it be? 72, 74? Okay, now in 74, the gradient is going to be minus 0.04 x minus 0.08 y. So this is the gradient, true? So that as they walk due east, which is in a plus x direction, then what they're going to do is okay, back off. So if we got the gradient into a I vector, oh, I see, okay, we dot it into the I vector, and all we're gonna do is pick out a minus 0.04x, and since x is minus 20 itself, then it's going to plug into a, so for 74a, what did people get, ascend or descend? Okay, 74, here we go. So we have the usual mountain, right? And so the elevation for the mountain, which sometimes can go higher or lower, so page
970.
970, z equals 2,000?
Yes.
2,000 minus 0.02 x squared minus 0.04 y squared. Okay, so del z is equal to minus 0.04 x I hat minus 0.08 y j hat. So did I find the gradient okay? So the directional derivative, so now we want to go in a unit vector which is equal to I hat, due east. 1 I hat plus 0 j hat due east, okay? So we have to dot these together. Del z dot u is equal to minus 0.04x. So del z dot u evaluated at x equals minus 20 is equal to is equal to 8. All right? Okay? Is that positive or negative? So that means it goes up, right? The rate of change, this is equal to dz ds. It's the rate of change of z as you go forward in s. Or it's equal to du. So it's a positive number. It means he's going to increase his elevation in this direction. Going to increase his elevation in this direction. Okay?
It's 0.8, right?
Is it 0.8?
Because it's 0.04. And I just times 20.
Yeah. 4% of 20. Okay, 20. Yes, sir.
So, like, I guess I may be applying way wrong thinking, but x east is down is negative, or east is positive x, west is negative x. So since x is squared and then in the positive direction, so any number that you're, well, never mind. Never mind, I'm answering my question, thank you.
Okay, any other questions I can answer? Sometimes they're easier than others. Now, if a climber uses a compass reading to walk northeast, will she ascend or descend, and at what rate? So B. So B, what we've established is that del Z is equal to minus 0.04 I hat minus 0.08 j hat. And now we have a unit vector now at the northeast, which is going to be 1 over root 2 times 1i plus 1j. So do we all agree that that is a unit vector in the northeast direction? Okay, Lynn? Monica? So all you have to do is dot those together and then evaluate it at the given point. So let's dot those together. du equals the gradient dotted into the unit vector, which is going to be 1 over root 2, and 1 times this is minus 0.04, and there's an x here and a y there, don't want to forget them. X minus 0.08 y. So this is now the directional derivative as a function of x and y. So now we need du evaluated at this point 20
It's 5.
and 5.
0.4 plus 0.8
I'm
is
just deciding that the altitude never seems to matter. It's a starting point.
The altitude shouldn't matter because it's the direction, right, that they're walking.
Oh, it does matter, perhaps in some questions. The change in elevation only depends on x and y, not your original z value, but because it's a rate of change. But they might ask a question that does depend on it. I don't see any yet. So now they walk northeast, so the points are at minus 20, 5. So x equals minus 20 and y equals 5. So let's evaluate this. It's 1 over root 2 times minus 0.04 times minus 20 minus 0.08 times 5. So 1 over root 2 times 0.8 minus 0.4. So final value is 1 over root 2 times 0.4. And it's a negative number, so it's a descending number, okay? Careful.
No,
No,
it's
that's
a
a positive
positive,
number, 2
because
minuses.
it's, yeah.
So it's a positive, this, okay, so it's ascending. Okay. And so the book has same answer on that, okay? Now part C. In what compass direction should the climber begin walking to travel a level path? 2 answers, a level path. Okay. In what direction? Now, in order to understand what direction we're talking about, we have to go back to Math 009. And we have 2 lines that are perpendicular. If the slope of this line is 3, then what's the slope of this line?
-3.
That's right, minus 1/3. True? So if 2 lines are perpendicular in 2 dimensions, their slopes are inverse reciprocals, true? So now in part C here, we have established the gradient. So del Z, part C, del Z equals minus 0.04x I hat minus 0.08 y j hat. Now we want to evaluate this gradient at the given point. So this gradient evaluated at the point x equals minus 20, y equals 5 is equal to 0.8 I hat minus 0.4 j hat. So did we evaluate the gradient at this point correctly, right? So this is a line that has a certain slope, and it's the direction of maximum change, true? So this is del Z. This is the direction del Z. Okay? Now, why don't we just actually plot it out in space to make it clear? So, from your given point, you're going to go to the right, 0.8, and you're going to go up, you're going to go down 0.4. So this is your gradient vector. So this is your gradient vector, and what's the slope of that line?
-1/2.
So m equals -1/2. Now, since this is the direction of greatest change, then it is perpendicular to the direction of no change, or constant. So what is the slope of this line? 2. So the slope of this line is 2, agreed? So if he walks up at a slope 2 line, then he will attain level path, because the level lines are perpendicular to the gradients. The gradients are perpendicular to the level lines. So all he has to do is go perpendicular to the gradient, and he will be on a level path. So if you have a m equals 2, then what is the angle involved? 2 to 1. So tangent of theta equals 2. So what is the angle that has a tangent of 2? Did I normalize the, what's that?
63 degrees.
63 degrees?
63.4.
63 degrees, so this angle is 63 degrees, and that's the right answer. So, this is specified as a angle bearing, which is 27 degrees east of north. This reads 27 degrees east of north, which is the same as 63 degrees up from the x-axis. So, just a bearing or a compass direction or an angle. So, the key point there was to be very, very clear that you understand that the level lines or level surfaces are always perpendicular to the gradient. And in 2 dimensions, it's just the inverse slope, reciprocal slope. So we did that. So it was good to have actually done a problem or two up at the front board, because that hasn't been done in a good long time. So are there any closing questions on section 13.6, which was an extremely important and very good section, because gradients are going to occur throughout the remainder of your work in calculus, however long that is. Even if it's only 3 weeks, you're going to see a lot more gradients. And you're going to see a lot more of the del operator. Remember, the del operator is just equal to d, is just a vector operator. It turns a function into a vector I hat d by dx plus j hat d by dy plus k hat d by dz. And it doesn't have to just operate on a function. It can operate on anything that you, pretty much that you care to have it operate on. So this operator has more purposes. It's a vector operator. Has more purposes than just deriving gradients. It's used for other things as well. So expect to see it some more in the next 2 or 3 weeks as it operates on different things besides a simple function. When it operates in a simple function, you produce a gradient. But you can operate on other things with the del operator. So the del operator is distinct from the gradient. It's just used in a straightforward function to produce a gradient. But it's an operator irrespective of what you choose to use it on. So now let's go to the next section, 971. And we're doing only one section tonight. So now we're going to do section 13.7. Now, we notice here we have a 3-dimensional surface, and if I have a 2-dimensional space, x and y, and I have some arbitrary curve in the space, and I introduce you to something called the tangent line at a point, then you found the rigorous definition of a tangent line at a point was a line that touched the curve at only one point. That touched the curve at only one point is the tangent line. Okay? Now, when we go to a 3-dimensional surface, we introduced something called the tangent plane. Now, if I choose a point on the surface, and I choose this point right here, then the tangent plane is the plane that touches the surface at only that point. So you see, we produce the tangent plane, true? Now, how would you suggest that we find the equation of the tangent plane? First, to find the equation of a plane, you only need to know a vector that's perpendicular to the plane, agreed? And a point. Well, we have the point already. So if we had a vector that was perpendicular to the plane, then we would be in good shape to find the plane. Now, at this point, can you suggest a vector that's perpendicular to the surface? Well, not so well, because what I've done is given you a situation where the surface is using one of the variables, z. So we don't really have the 3 dimensions anymore. So it's not quite as clear as if I was using a function that was really a function of all 3 derivatives. So what I've done is sort of make a picture of what it is that we're looking for as the 3-dimensional analogy of a tangent line. What we're looking for is a tangent plane. So now I'm going to take away my artificial construction of a surface, and what I'm going to really have now is a 3-dimensional function that's everywhere in the space. So if I describe this surface, say I can describe it in 2 ways. One, I can give you z as a function of its xy point under it. But the other way that we've learned to describe locations in 3 space is we simply take the r vector and the r vector will describe any position that we care to have on our surface. So if we have some surface and we want to point to a point on that surface, all we do is give its r vector, which takes us right out to the point. Okay. And at this point, we can, at this point, let's say that this point is right under there, we can find the tangent, or the rate of change of r. And the rate of change of r depends on what curve that we have chosen. So on our surface, the first thing that we have to do is choose one of many curves that are in the surface. So here's one curve that's in the surface, there's another curve that's in the surface, here's another one. So indeed there are infinite number of curves that are in our 3-dimensional surface. So any 3-dimensional surface is just full of curves, an infinite number of them. So we're going to select one curve in particular. Now, the requirement that I want to make on the tangent plane that we end up with is the following. Every 3-dimensional curve that I can form on the top of this surface that goes through this point that I'm interested in, every 3-dimensional surface every curve that I form on this surface must be tangent to this plane. Now, a way of establishing tangency is that every curve that goes through this point indeed will have a tangent vector. Indeed will have a tangent vector. So let's find that tangent vector. Say I'm interested in this particular point. Then at this point, say I'm interested in this curve. So at this point, I'm interested in this curve. I'm selecting this curve along the surface, and at this point, this curve will have a tangent vector. It will point in the direction of the curve, agreed? Now this tangent vector, I'm going to require, the definition of my tangent plane is that this tangent vector is in the tangent plane. This is a tangent to the surface at this point in this direction. I'm going to require that my tangent vector have this tangent embedded in it. And if I change to some other curve, such as this curve, then it will also have a tangent vector at this point. So I'm going to require as my definition of my tangent plane that it contain all the tangent vectors for all the curves that go through this point. That all the curves that go through this point, each of them will have a tangent vector. And my definition of my tangent plane is the plane that contains all of those tangent vectors. All of those tangent vectors will be contained in this plane. And that's the definition of the tangent plane. So let's touch base with the book, which probably has a bit better drawing.
The drawing's very two-dimensional.
Aye. Well, on page 971, what we have is the surface. And as you see, it's a function of x, y, and z. And you pick your point, P0, that you're interested in, and you pass some number of curves through that point. Each one of those curves will have a tangent vector. And your tangent plane will contain all of them. Your tangent plane will contain all of them. This is another way of saying that the tangent plane touches the surface at just one point. Is equivalent to saying that the tangent plane contains all possible tangent vectors that come out of that point. Is equivalent to saying that it touches at just one point. If we say that it touches at just one point, or we can say that it contains all possible tangent vectors that come out of that point. If we say it contains all possible tangent vectors that come out of that point, then we're in a position to formally derive the equation of the plane. Now, what I did was sort of intuitively tell you that this three-dimensional function is like the three-dimensional function in the room for the temperature. And if I have a point in this room, then it will have a direction of greatest temperature increase. And that direction will be the gradient direction. So at any point in the three-dimensional space, you can have a direction of maximum increase. And what we've alluded to before is that the direction of maximum increase is always perpendicular to the level curve. Now, a tangent line is not changing its value as it goes through the point because it's flat with that point. That's what a tangent is. Even in 2 dimensions, it doesn't change its value as it goes through the point because it's just touching the point, it's flat. So since it doesn't change its value, then you would suspect that the direction that is normal to the tangent plane is going to be in the direction of the gradient. That's what we would expect. But what we have to do is to make a formal proof of that. And we very rarely do formal proofs in here, so we perhaps do. So we can actually do one. So if what we have is that the r vector is equal to xi plus y plus z, and let's take the r vector to be parameterized as a parameter t, so that the r vector is a parameter of t, so it's equal to x of t, I hat, plus y of t, j hat, plus z of t, k hat. So now I've indicated that my tangent vector is going to be in the plane. And the tangent vector points in the direction of the increase of r, because the r ds is the definition of the tangent vector. So as you move along your chosen curve C, if you take the derivative with respect to progress along that curve, then you're going to be moving in the direction of the tangent vector. So if I take r prime, then I will produce a r derivative vector which is parallel to the tangent vector. So the direction of r prime is the same as the direction of tangent. This is more clearly seen in 2 dimensions. If you have a curve that goes like this, and if at this point you have an r, and up here you have an r, another r, and so you have some change, delta r, then delta r and tangent are in the same direction. dr, the change in r, and the tangent are in the same direction, because this is the vector delta r that connects r1 and r2, if you will. So in 3 dimensions it works exactly the same. The r derivative is in the tangent direction. So you just take the derivatives of the 3 components, and you have a vector that is in the tangent plane. Now, this surface is described by some function that I haven't yet mentioned, but this function that is described by, let's just call it f of x, y, and z. So let's continue looking for an equation of the plane that is tangent at that point. And to do that, then let's take the total derivative of f with respect to s. In this direction, okay? And the total derivative with respect to s is 0. For a reason I don't remember. Oh, because it's a constant surface. Okay. That's one of the restrictions that I failed to mention. We're not talking about just any surface here. We're talking about a subset of any surface which is called a level surface. So that all values of the function are equal on this surface. So this is a restriction to what we call a level surface. Okay? So when we are on a level surface, we would expect that the direction of greatest change is in the direction of the gradient, and that the gradient to a level surface is perpendicular to the surface. So if it's a level surface, then we're even more strongly looking for our gradient. So what we have is that f of x, y, and z is equal to some constant value c. So if f of x, y, z is a constant, then what I want to do is take the total derivative of both sides, d by dt. So I want to operate on this entire equation with d by dt. So, AJ, what is d by dt of a constant?
Zero.
So now we're going to use the chain rule here. So it's df dx dx dt plus df dy, and these are partials, dy dt plus df dz dz dt. Now, this can be expressed as a dot product of two vectors. This is df dx I hat plus df dy j hat plus df dz k hat dotted into dx dt I hat plus dy dt j hat plus dz dt k hat. Now, if you dot these two together, then you will produce the total derivative. So dot the two together and see what you get for the first term. df dx times dx dt. And what you get for the second term? df dy dy dt. So this 0 can be written as the dot product of these two vectors. So it's del dot f dotted into, now please note that this vector here is this vector. Is it not r prime? If r is x plus y plus z, then if I d by dt this, I get dx dt, dy dt, and dz dt for r prime. So if r is xi plus yj plus zk, which is the position vector, then dr dt is equal to dx dt I hat plus dy dt j hat plus dz dt k hat is r prime. So this vector is r prime. So what I've established is that the dot product between the gradient and r prime is 0. Now if the dot product is 0, what does that say about the angle between the two? 90 degrees. So I say the angle between the gradient and r prime is 90 degrees. But we've established that r prime is tangent to the surface, because r prime and t point in the same direction. So we've established then that the gradient is perpendicular to the tangent of this curve. But this curve was chosen totally arbitrarily. I could have chosen any other curve through the point to be my c, and the c drops out because you take the derivative of it, or the c for the constant. So it doesn't matter which curve that you take, you're going to have the same result, that the gradient is perpendicular to the tangent to that curve for all possible curves that pass through that point. Therefore, the gradient is perpendicular to the plane that contains all of those tangent lines. the plane that contains all of those tangent lines is a tangent plane. So this is a formal proof that the gradient is perpendicular to the tangent plane. So that puts us in a position to completely calculate the equation of the tangent plane. So if you have some surface, and you take some tangent plane to it, then that tangent plane is going to have a gradient. The gradient is to the surface. The surface is f, x, y, z. And now we've established the gradient. We also have the point. We have the point x0, y0, z0. So if you have a normal vector to a plane, and you have a point in the plane, can you find the equation of the plane? If you have a point in the plane and a normal vector, let's go back to chapter 12. Can you find the equation of the plane? If you have a normal vector to a plane that is ax, is ai hat, plus bj hat, plus c k hat, if this is a normal vector to a plane, and then you have some point in the plane, say x0, y0, z0, then you can produce the equation of the plane as a, x minus x0, plus b, y minus y0, plus c, z minus z0, equals 0. And we did this several times. Because if you have a vector n, and some point x0, y0, z0, and some arbitrary point x, y, and z, then what you have here is the vector x minus x0, y minus y0, z minus z0. Here you have a vector a I plus bj plus ck. Now, if this vector is in the plane, and this vector is perpendicular to the plane, then what is the angle between the two vectors, one of which is in the plane and one of which is perpendicular? 90 degrees. So that means the dot product between this vector and this vector is 0. So 0 equals this times that, a, x minus x0, plus this times that, b, y minus y0, plus this times this. So the equation for any point in the plane, x, y, and z, when there's a known point in the plane, x0, y0, z0, and a known normal to the plane, are the components of the normal to the plane, a, b, and c, times the components of a vector in the plane, x minus x0, y minus y0, z minus z0. So we've done this several times before. So if we have the function and a point, then we can establish the equation of the plane that is tangent. Yes, sir.
Sorry, I'll let you finish first.
Well, I just came to a stopping point and ready to reach an example. So that can be regarded as the right time.
All right, so a sphere would be a level surface.
A sphere is a level surface.
So the direction of greatest change is perpendicular to any point. So
It's
the
a
direction
radial
of,
direction. Yes.
so the direction of greatest change.
Direction of greatest change. Now be careful, because a sphere is using one of the variables, z. So we haven't covered that yet. We're coming to that next, so you do have to wait. Because what we have done is deal with a full three-dimensional function. And a sphere, well, the radius is a three-dimensional function. So the direction of greatest radius change would be a tangent plane. I think that's consistent, yeah. Okay, the radius is evaluated as a function of all three variables. So continue. Okay, your question?
So I guess I thought that the gradient pointed towards part of the shape. And this is saying that the gradient is pointed perpendicular to a sphere at any point that you're
Yes,
at.
because you have to ask the gradient of what? Now, when you say the gradient was pointing in a direction on the surface, is when you are using one of the variables as your function. In other words, if you take a sphere, or a half sphere, hemisphere, and you let z be a function of x and y, agreed? Then the gradient points in the direction of increasing z, because z is what is increasing. So that's 2 dimensions. But if you look at a 3-dimensional sphere, and then what you're increasing is the radius of the sphere. The radius of the sphere is a function of all 3 dimensions, not its height above the xy plane. So when you have the sphere in 2 dimensions, say a hemisphere, which looks like this, then z is some z of x and y. So if you have a direction, if you're at this point and you want to go to a higher z, then you go in and you go to a higher z, agreed? So this is because z is being used as one of your variables. But if you have this sphere, and the rho for this sphere is x squared plus y squared plus z squared, is rho squared, true? Now, rho is what you're increasing, not z. So if you go to some larger rho, then the gradient of rho is straight out. The gradient of rho is straight out, because now you have a function of all 3 dimensions. Here you have 1 dimension being a function of the other 2. So the gradient has a direction. So it has to do with the number of dimensions that you'll have. Okay? So let's look at an actual example. Consider the ellipsoid on page 972. X squared plus 4y squared plus z squared equals 18. Example 2. Page set 972. So the function of x, y, and z is equal to x squared plus y squared plus z squared equals 18. So the function of x, y, and z,
4y squared.
4y squared, okay, I'll get there. Okay, now this is certainly a surface of constant value, agreed? So it's some surface of constant value. So the normal plane is going to have in the normal to the plane is going to be the gradient of f, which is 2x plus 8y plus 2z, is going to be the gradient of f, where we have our usual I hat, j hat, and k hat. So if we look for the equation of the plane, then we have to have a point. And so we're going to evaluate this at the point. So the equation for the plane is going to be 2x0, which is this evaluated at a point, minus x minus 0, plus 8y0, y minus y0, plus 2z0, z minus z0 equals 0. So this is the equation for the point, where this normal dotted into a vector that is in the surface and then evaluated at x zeros is going to produce the equation for the plane. Okay. So that's how you handle these examples. Okay. And the next is to go to the subtopic that Stuart alluded to at the bottom of 972. Suppose that you have a surface of the form z equals function xy, where one of the variables is actually the function. So it's really only a function of two variables, but yet it's a three-dimensional surface. And it's the one that we just started with in our example. And the author makes a very, very clever approach at this point, because he decides that this is already a solved case. Because all you have to do is say that your function of x, y, and z is going to be z minus the function of x and y that you're given. Because if I move the z to the other side, then on this side I certainly have all three variables, z, x, and y. True? Well, you say, hey, wait a minute, that's 0. Well, that's all right, because we're used to having functions of constant value. So this is just a function of constant value 0. So now that we've established this function, then we treat it exactly as we did when we had f of x, y, and z. And the normal to the plane is going to be the gradient of this function. But you see, the gradient is now going to break into two parts. We can turn it the other way around, and maybe he does handle the minus sign over there. No, he handles it the same way. So it's going to be minus df dx I hat minus df dy j hat. And now it's going to be the derivative of this with respect to z. What's the derivative of this with respect to z?
Or 1.
Just 1. So it's plus k hat. So you see, when you have this situation where z is the surface, and one of your variables is used as a surface, then you always get a constant k in the gradient, which means it always has a component that's pointing up out of there. So now that we've established a gradient, we can write this in terms of a, b, and c will always be a constant 1. So it simplifies in that respect. So let's take an actual example. On the top of 973, we have the example 2, 973. We have z equals x squared y. So we form the function f of x, y, and z equals z minus x squared y. So 0 equals del f, because f is 0. Okay? Well, maybe that's too strong a statement. So we can take del f is going to be minus 2x y I hat minus x squared j hat plus k hat for del f. So if we want to evaluate this at the point 2, 1, 4, so del f evaluated at x equals 2, y equals 1, and z equals 4, z doesn't matter, is going to be minus 4 I hat minus 4 j hat plus k. So we indeed found the, and this is the normal to the tangent plane. So if we have a point in the tangent plane and the normal, then we have our coefficients a, b, and c, and we form the equation of the tangent plane. So notice that in general, this function is going to take the following form. If we have the del of f in general is going to be f of x I hat plus f of y j hat plus a single k. So we had this earlier in the form of df dx and df dy. And these are going to be minuses, so that's okay. And if we dot this into some vector that is in the plane, which is x minus x0, I hat, plus y minus y0, j hat, plus z minus z0, k hat. So if we form the dot product of these two, is going to be 0. So the dot product of these two is going to be f of x, x minus x0, and this will be the equation of the plane, minus f of y, y minus y0, plus z minus z0. And if we solve this equation for z, we're going to get z equals z0 plus f of x, x minus x0, plus f of y, y minus y0. Now, the only thing to say one more time is that z0, since z is a function of x and y, by definition, then z0 is a function of x0, y0. Because z in general is a function of x and y. So this is the function of x0, y0, plus f of x, x minus x0, plus f of y, y minus y0. So this is in general the equation for a plane that goes through a surface of the form z equals function of x and y, where one of the variables is used as your function through the point x0, y0. This will give you the equation of that tangent plane. Now, what the book points out is that you have seen this before. You have seen this before as a linearization of the function z about the point x and y. Because when you linearize a function, say in 2 dimensions, then you take the value of its derivative right here, which would be f of x at this point, and you multiply it by some small amount of change in x. And then you add to it the value at the 0 point. So this is called the new value. L is equal to the function at x0, which is the function here, plus this amount, which is delta x times the derivative evaluated at x0. So this is the way that we linearize any function about a point x0 by using its derivative. And this is exactly what's happening here in higher dimensions. Here you have the original point about which you are evaluating the linearization. Here you have the derivative and the linear increase in x, the derivative of y and the linear increase in y. So what you have here is the same equation that you would have if you took a linear approximation about x0, y0. So the function for z is a function for the linear approximation. And that's brought out for you at the bottom of 973. Now, the last topic, and we're done with this, is 974. And it's one that you have seen quite a few times before. So Lynn, could you read the title to us on the topic on 974?
Using gradients to find tangent lines to intersections of surfaces.
Okay, now, we've talked before about the intersection of two planes. And how do you find the line that is the intersection between two planes? Well, the line that's the intersection between two planes is in both planes. It's parallel to both planes. Therefore, that line is perpendicular to each of the normals to both planes. So if you have two intersecting planes, if you have these two intersecting planes, then this line is in both planes, so it's parallel to both planes, so that this line is perpendicular to the normal to this plane, and it's perpendicular to the normal to that plane. So it's at right angles to both of these normals. So a line that is on the intersection of two planes is perpendicular to the normals to both planes. So now that we go to curved surfaces, and we have a curve that represents the intersection between our two planes, then if we take the normal to this plane and the normal to that plane, and we ask for a vector that is perpendicular to both of them, then it's parallel to their cross product. It's parallel to their cross product. So what we do is cross N1 with N2, and we will produce a vector that is in the direction of the intersecting line. Now, the only restriction here is that that line is curving, whereas in our previous work, that line was straight. So in our previous work, we found the final solution. But now this solution is only good at a local point, because if you move to another point, then everything has curved. So you have to reevaluate it. So all we can do at this time is we can find the equation for a tangent line at a point, as if they were straight planes and not curved planes. So that's what we have to do, is to find the equation for a tangent line, because what we produce is a vector that is perpendicular to both of the surfaces at that point. And our line now has a vector and a point, so we can use a parametric equation for a tangent line at that point. So we finished this section. It's in your hands now. Set to do the homework. We're out of here, and the test will be dispensed by 3 o'clock tomorrow afternoon, as long as you've signed off.
Now, I got mine before I signed off on your message, so is it not supposed
You
to?
got the test that I haven't made up yet.
That's why I said I got an email from you that said warning on test 2. And but this one said it was 15%. It didn't say it was.
Well, I haven't changed that yet, but I haven't sent any emails out, so I wonder who's sending you emails in my account.
I don't know. I got an email from you.
Test 2?
I won't open it and send it to you because I have no idea
I
what it
didn't
is.
send that email.
Just
Don't
screenshot it and send it to me.
AJ sent that email.
It's in WebTyco.
Okay, I'll look for it
How
myself.
can I send something to I don't know the password to my own?